Alrighty, y'all, welcome back to Michelle's version of calculus with 3.2, and we're going to be talking about implicit differentiation. You're gonna have to stick with me here. It's gonna be a little confusing, but it gets better. Alright, so first thing first, we're gonna review the difference or learn the difference between explicit equations versus implicit equations. And I think the best way to see this is with an example. So for explicit equations, y equals e to the x explicit because you can easily solve for the variable x or y or whatever. You can solve for that variable very easily. However, with an implicit equation, example y equals e to xy, you aren't able to specifically solve for y or x, like in this equation. You couldn't do it. Or you couldn't solve for y in this equation. And basically that would be implicit. And if you're ever really confused, just implicit will always have x's and y's, like doing crazy things on both sides. All right. So yeah. So all right. So let's go for little examples, or I guess not examples, but some things here. So let's say when it comes to the differences between differentiating between x's and y, we know with x, so we know that like the d over dx of x equals 1. However, a derivative of y actually just equals y prime. Or you can see it written as dy over dx, and that's the way that I will more than likely be using throughout the video. All right, and so then when you have the d over dx of x to the third, we know that would give you 3x squared according to our lovely power rule there. That's right, power rule. But then of course since you derive y to the third, it's going to give you 3y squared times dy dx, or once again y prime, either one works. So basically when it comes to doing differentiating y, you will still use power rule. As you can see here, we are still using the power rule to get this first answer choice, but you will just multiply that times dy dx or y prime. So yeah. Alright, so we're going to go to an example, and we have some lovely steps to kind of help follow along the way for this example. Alright, so our example is y to the third minus 2x equals x to the 4 plus 2y. And of course, we are going to find the derivative using implicit differentiation because, as you can see, there is no real way to solve for y or here specifically. So we're going to use implicit. Alright, so first step is to differentiate both sides. Can I move this? I can't. It's all good. First step is to differentiate both sides. So we have we'll have 3y squared times dy dx, again, or y prime. I just prefer to use dy dx, and I'm doing this in purple. We can use our regular power rule for this, since it's just an x. It'd be minus 2 equals 4x to the third plus 2 dy dx. Plus 2 dy dx. Alright, so now we use, let me write this down. So now we move all y or dy dx. Dy dx is to one side, which we will do in this orange color here. Alright, so we would do 3y squared. Let me just put it to 3y squared times dy dx minus 2 dy dx equals, and we're gonna move this plus 2 over. It's kind of just algebra in your head, guys. 4x to the third plus 2. We do that, and now we're going to factor out our y primes, or let me just write it again, dy dx's. So when you factor those puppy out, 2, you will have dy dx times 3y squared minus 2 equals 4x to the third plus 2. And then you just kind of divide it out over here. Pink star. You would divide it out. We'll use yellow. Ooh, that's too similar to orange. We will actually be using green. So 4. Again, we divide it out. So it would be dy dx equals 4x to the third plus 2 all over 3x squared minus 2. And that would be your final little thing here. And you can use this puppy to approximate the rate of change at a point for an implicit function. And yeah, that is all for implicit differentiation.